Okay, good morning, welcome back. So today I will start covering graphs, and I know many of you know at least the basics about graphs. So I will just go quickly through the first few slides to make sure that everybody is aware of the terminology we use, and then I will go cover other topics. So first thing is the definition of a graph. A graph is simply the given of two. Is defined by giving two sets, a set of nodes, V, and a set of edges, which are really simply pairs of nodes from V, okay? And that represents essentially, a graph represents a binary relation, okay? So that's what you have here. So the set edge E is the edge, is a set of binary pairs UV that satisfy a certain binary relation. That's all really there is to it. And so terminology, here are a couple of examples. On the left side here, you have a binary relation that's not symmetric. So you have a directed graph. And on the right side, we have an undirected graph where the relation is symmetric. So terminology, we say that when UV is an edge, you say that U is V is adjacent to U, and then the edge UV is incident to U and V. Then we have a disconnection plan between outgoing and incoming edges in directed graphs. Degree of a vertex is the number of edges that go out of a vertex, of that vertex. You can also distinguish between incoming and outgoing degree. Let's move to the other. So here, now one definition that's important in what we do is the adjacency matrix. So you're given a graph, you define this matrix A associated with the graph, which is defined as follows. So it's really defined here. So you define Aij to be 1 or 0. It's 1 if I and j are adjacent. So in other words, if ij belongs to E, if it's an edge, and 0 otherwise. Really simple examples here. This is a directed graph. And you can see here, if I take the first row, let's take, for example, the first row, and just to, for illustration, the first and third row, here for one, you have 1 is connected to 2 only in the first row, and then vertex 3 is connected to 4 and 2. 2 and 4, I see it here. And this is the same example, but now with an indirect graph. So you have now a symmetric matrix. The matrix becomes symmetric. So the other definition I want to emphasize is the definition of a path. That's a sequence of nodes that are connected by an edge. Okay, the length of the path is the number of edges in that path. The cycle, I don't think we use that too often. Here, for example, this is a cycle. You know, you go from 1 all the way down and you come back to 1. And here is a path. And the length of this path here is going to be 1, 2, 3, and 4, just to count the number of edges. Okay, those are a very quick overview. This is a very quick overview. Then there's definition of connected and unconnected. We're not going to see too many of those. So now let's go to specifically look at the relations between graphs and sparse matrices. There's a strong connection, as we saw now with these examples I showed you. Here is the example we had before. So this adjacency matrix typically would be a sparse matrix, right? We have sparse graph. Sparse graph is a graph where you have the degrees are all not too large, they're small, okay? So that's very similar to saying that the adjacency matrix is sparse, that's all. So this is just an exercise given to show the pattern of the matrix here. I don't have to look at that. This one is an example where I show the adjacency, show a matrix, and I'm asking what is the adjacency graph of this matrix. I have it here. let's see, I have it in sparse. So I'm going to start MATLAB. I haven't started it yet. So I'm not there. I always use it without the desktop because I can change the font and so on. So here I'm going to go to sparse. And I know they have a matrix called load math, which is just a small matrix, which is exactly the one I showed you. Oops, it doesn't seem to exist. Where is it located here? Small, okay. There we go, this is matrix. That's not quite what I had in mind, but it's okay. So, oh, match 6, okay, where you go? You know, here, that's the matrix, exactly the matrix we saw here. Exactly this matrix in here. And what I will do is, if you want to think about this, so think about the graph associated with this. I'm going to say define the graph. Use MATLAB's graph because we're going to get used to this, and then I will just take this as a matrix here, and then I will say plot the graph. Show me the graph. Plot G, and they will show me the graph. But I have to figure it out. Where is it? It's located somewhere here. There we go. That's the graph. And if you think of the matrix we just saw, for example, if here, if I this here and here, for example, if I look at node, the one that's really has a high degree is this one here, 3, and you can see it's connected to 1, 2, 4, 5, and 6, and all essentially everybody else except 1. So I'm sorry, I meant 2, and 4, 5, 6. So everybody else except 1, for example. Okay. Well, this is just an illustration. Now, there's a notion of isomorphism. Two graphs are said to be isomorphic if you can map one to the other by a simple permutation, essentially a relabeling of the nodes. Okay, for example, these graphs you can see, these 3 graphs are isomorphic. They look different because they're essentially drawn in a certain way, but they are the same graph. Okay, but determining isomorphism is actually not an easy problem. It's a hard problem. You can figure out why that's the case. It's not that easy for large graphs in particular. In fact, MATLAB provides a function to identify isomorphisms. Just a couple of words about bipartite graph representations. So very often we think of graphs the way I just described now for standard problems. There would be n by n, and the relations are very simple. But sometimes it's actually useful to use a totally different model. This is one of them. Okay. And that one, in this model, I use on one side, these are rows, and these are columns. And there will be a connection between a row and a column if Aij is different from 0. So there's absolutely no connection between rows. It's all different objects. So we call this a bipartite representation. And you can imagine why this could be useful. It could be, for example, useful if you have rectangular matrices. Then it makes, there's no I and J don't have any, see, they're not the same objects in that case, right? So you have to do something different. And that's where this could be useful. So I'm not going to use this too much here, but you have to keep in mind that this could be useful in some situations where, for example, rectangular matrices, or even for regular like n by n matrices, square matrices, this is sometimes used. Okay. All right. So the next thing I will ask is about interpretation of graphs, with respect to matrices. So, for example, if I gave you 2 adjacency graphs, A and B. So you have two graphs associated with one with A, one with B. So what is the graph of A plus B? Now this is a question. It's simply a graph which has the same number of vertices, so it's the same vertices, but the graph is the union of the two graphs. So you have an edge between I and J if there's either an edge in A or an edge in B, right? So that's really simple in this case. The graph of A transpose is fairly simple when A is non-symmetric, otherwise it's the same, obviously. When A is non-symmetric, you just reverse the directions, right? You just change the directions to the opposite for each edge. That's easy. How about this one? This one requires a little bit of thinking. So what's the graph of AB, A times B? So we are interested in looking at that because we're going to take a look at fact graphs and path lengths. So so powers of matrices and path lengths. So this will help explain a little bit what this thing. So I'm going to explain this by, I think I have something called TMP, which I prepared here. So this is about AB. So let's look at the product AB. And okay, so Cij, this Cij is equal to, to the sum of Aik by Bkg, right? Bkg. So if Aik is non-zero and Bkj is non-zero, then you have one item that's added to that location Ij. So there will be non-zero. So there will be, here is a representation of what is happening here. So if there is an edge between I and K, so Aik is non-zero, and if there's an edge between K and J, meaning that Bkj is non-zero, then there will be an edge between I and J, all right? In fact, if you add them, you add these numbers here, they will tell you exactly how many edges you have. So if you, this is the products, you remember that the Aijs or Bijs are all ones or zeros. So they will be all ones, so we multiply them will be a one. But if you add them, they will tell you how many edges you have. So that you can count the number of edges that you would be in between I and the number of possible edges you have to go from I to J. So this is like a path going from I to J. How many possible ways you can go from I to J with the path of length 2 going from I to J, K in B in A and K to J in B. So this is not as critical in this, but we'll display it. You can exploit this later. So questions about this? That's we're going to use something very similar to this now when we look at paths of arbitrary length. Okay, next. So here it is actually. What is the graph of A to the power K? If I take the graph, take the agency graph A, and I ask the question, what is the graph of A to the power K? What are the well, first of all, what is the agency graph? What does A to the power K represent? So here's the theorem here, which says the following. This result from this question here comes from the example I gave you. So again, I'll leave that out. But now here's the main thing I want to focus on, and that's the theorem here. Let A be the adjacency matrix of a graph. Okay, so it's zeros and ones. Then for K non-negative, so for K positive or zero, and the vertices, and for two vertices U and V in G, the number of paths of length K, starting at U and ending at V, is equal to A to the power K Ij. So the Ij entry of A to the power K. And that the reasoning here is fairly similar to what I just described for the simple example we showed earlier. So I'm going to try to move this a little bit to the left side. Okay. It's gone now. Oh, okay, right. So if you have, to build a path of length K from I to J, you have to go with a length of a path of length k minus 1 and add one edge. So it's all possible paths from one of length k minus 1, which is the previous power. So this is an induction argument, right? So you take you take the aij, bij from, so b here would represent a to the power k minus 1, and then add that, exactly the argument I had earlier, and add that edge, and then you construct all possible paths of length k. So that's really a very simple argument. It's very powerful, by the way. This theorem is very useful. I know, I think, was it Tim yesterday mentioned this example where you have counting triangles. Triangles are just paths of length 3, right? So you can count paths of length 3 that are cycles. So you go from I to I with a length 3. So you could use this theorem, which is very simple, to count the number of triangles. Okay. Now, another theorem that's important is the Perron-Frobenius theorem. And then here I'll remind you of this definition. A matrix is reducible if you can permute it. So rearrange essentially relabel the nodes so as to put it in block upper triangular form. That's a matrix that's reducible. That's reducible. Irreducible is when you cannot do that, essentially. Here's an illustration of that. So here is a matrix here. It has been reduced by permutation. So originally, this was completely imagined. You had initially completely scrambled the matrix, but you don't see this pattern. You don't see that this is a block upper triangular matrix, okay, when you have it. But then there are algorithms that will allow you to unravel the structure, all right? Connected components, essentially. These are connected components. So you take that algorithm and then you permute the matrix to put it in this form. So this amounts to just essentially permuting rows and columns in the same way. That's sometimes possible, and that in that case you say that the matrix is reducible. And that to the graph, this is what actually this corresponds to. You have little pieces that are pointing in one direction to some to the other. This one, for example, points to this block and this block, which is these two subgraphs, okay, but not the other way. So, and that corresponds to simply in the graph finding these components, right? Connected components. So here's the main theorem that I wanted to mention. So let's suppose you take an irreducible matrix. So you cannot put it in this form. You cannot decompose it in this block form. Then, so it's also non-negative. So n by n, irreducible. Then you could say that it has one real positive eigenvalue, lambda 1. So the largest eigenvalue essentially is lambda 1, such that lambda 1 is a simple eigenvalue of A. Lambda 1 admits a positive eigenvector U1. So the components of the eigenvector are positive. It's strictly positive. Okay, it's very, very important. And the lambda 1 is the largest eigenvalue. That's really, so essentially it tells us the spectral radius is exactly an eigenvalue. So it's lambda 1, the spectral radius is the eigenvalue lambda 1, okay? And then you associated with that eigenvalue, you have a positive eigenvector. So it's a very important theorem because it's used for proving a lot of things, but also that eigenvector is often associated with probability distributions and other things. Okay. Okay. So, for example, you can easily show this if a graph is deregular. A deregular graph is when you have a graph that has, for each vertex has exactly the same degree. Okay. That sometimes happens, you have exactly the same degree for each vertex. So in that case, the spectral radius of the, well, I said deregular graph. I should say the spectral radius of the agency matrix associated with a deregular graph is equal to D, exactly D. And that's not very complicated to see here from not very complicated proof. Uses Frobenius theorem. So now, as an application to this, you can see Markov chains. So there's a section you can take a look at in my old book on eigenvalue problems here. You can, if you have the lecture notes, your point here will take you to the site. So I don't want to do it now, but okay. So P is a matrix of probability, so transition probability. So you go from I to J with a certain probability for a fixed, let's say fixed I. Okay, so the sum of the aij's are therefore equal to 1 because the sum of all probabilities have to be equal to 1. So the row sums are all equal to 1, right? So if you imagine you could jump from I to J with a certain probability Pij, then the sum of the Pij's have to be equal to 1. So that's the main condition. The Pij's are non-negative. Okay, so the right eigenvector, one vector of all ones is the right eigenvector because the row sums are all ones. And the most important thing is the row vector pi. Pi is now a row. Okay, so it's a row of length n. It's a left eigenvector for P, for matrix P. All right, it's the corresponding left eigenvector associated with eigenvalue 1 is called pi, okay, row vector. And that has an important meaning. It's the row of stationary probability. So if you have I mentioned to you the example of a triangle, the Markov chain and a random walk on a triangle. We have a triangle mesh, and you have imaginary particle that could move to any of the neighbors with certain probabilities. So they have to sum up to 1 in each case. And you ask the question, after a very long walk or after a very long time, what is the probability of finding that particle at any particular node, at any given node? And that's given by pi. That's this pi here. So that's what Markov chains are about. And so the matrix P that you see here is said to be stochastic, which means it satisfies these three conditions. So the Pij's are non-negative. They sum up to 1 for all the rows. And this is an assumption, an additional one. There's no zero column. That's the stochastic matrix. Okay. So the stochastic, now this is about this spectral radius. The stochastic spectral radius is less than or equal to 1. So these are all just some consequences. And there's an example in here, which is a very simple illustration. You have a college fraternity that has 50 students at various stages of college. So freshman, sophomore, junior, senior, etc. And so they also have other things you see in the next table. There are 6 potential stages. So these 4 ones that I mentioned, plus graduated or dropped out. Okay, so 6 possible outcomes. And the question, this thing gives you the probabilities of going from one stage to the next. So freshman to sophomore, these are all the probabilities that you have, and junior to freshman, etc. And so you can build up a matrix of probabilities given this. And then you ask the question, what are the probabilities of a student being at any given stage? It's exactly the same question of that question about the Markov chain, on the random walk on the grid. So, and that you can then set that up. And then this is not actually complicated. To give that as example when I teach this class on matrix computations, sparse matrices. Okay. All right, good enough. So just a couple of words about hypergraphs. So just like bipartite graphs, hypergraphs could be also useful in some other situations. They have been actually present for a long time in the VLSI world, okay? But they came to the scientific community, scientific computing community, when people started looking at graph partitioning and how to optimize matrix vector products for large sparse matrices. It turns out that the usual way of partitioning a graph by simply putting nodes roughly with the same number of nodes, are trying to minimize the edge cuts, what is called edge cuts. So number of times you cut an edge when you after you partition the graph. It turns out that it was not optimal. So you can, if you do matrix vector products, you want to minimize the amount of communication that takes place, and that seems to be that turned out to be a good model. Hypergraphs. So what are hypergraphs? So these are just some of the motivations about this. And also, when you have rectangular matrices, also they could be used for that. They could be used for matrices that have completely irregular patterns, very non-symmetric patterns. In this case, they could be useful. So what are hypergraphs? So instead of having an edge, so an edge consists of a pair, UV, right? So it's a collection of vertices and a collection of pairs. Here it's a collection of vertices and a collection of sets. Instead of having pairs, you could have more general sets. Here's an example here. These are all, the vertices are the letters, A, B, I'm sorry, no, the opposite. So the vertices are just the crosses, the blue crosses here. These are all the vertices. You have 8 of them, or 9 of them, apparently. Okay, and then with each, I have these sets here, this one. This is called the net. It's a collection of vertices. They have 2 vertices in here, and I put an E symbol associated with that. So this would be my net in E here. This one has 3 vertices, etc. So here's how you can represent that. Here the vertices are here, okay? And then instead of having the same number here, these are the nets. So what A, for example, have 1, 2, 3, and 4. This is A. It has exactly these 4 here. Okay. This is my A. All right. This is A. It has these guys here. And if I look, for example, at C, it has 1, 7, 8, 9. C is this one here, 7, 4, 8, and 9. That's this one here, etc. That's the, this would be the equivalent of the adjacency matrix. In this case, it's just, we call that a Boolean matrix associated with the hypergraph. Okay, questions so far? Let's see if there are any, okay, questions here. So these are just really basic definitions. And again, I'm not going to be using hypergraphs in the rest of the talks. One thing that has come out as an important application of graphs is computational graphs. So these were actually invented a while ago, right? It was not really at the time of automatic differentiation. I think it was invented by Andreas Grevand, if you remember that, Tim. Right? He was probably at CSRD for a while, I forgot. But he was working on how to put automatic differentiation in codes to solve nonlinear systems or in optimization. So at the time, you either could get your Jacobian explicitly. The Jacobian is, you can compute it because you know how to differentiate, or otherwise you're out of luck. It's very difficult. And people talk about symbolic differentiation. But that's very difficult when you have huge like computational graph or a huge system of nonlinear equations where you have very complicated functions involved. So they come up with this idea of differentiation, automatic differentiation by using computational graph. So computational graph is a graph where at each node you have a certain computation, okay, that depends on things that come from, you see here there's a graph, you can, this B of X, Y, Z depends on the vertices below it. So to compute this, you need these functions to be evaluated. The functions are located here. For example, this F needs A and B to be evaluated. So you have a graph, a tree that's like that. And you can easily build, you can easily evaluate f by following the graph from the bottom up from the leaves up to the top to the root. Okay, that's easy. So here's an example here. So for example, if I want to evaluate this, I can split it into three different atoms or components. So z is x plus y, and then v is y plus 1. This is z. This is y. This is v. Okay, and then g is z minus 2 times v, right? So, and the graph is here. Okay, so the question is, how do you compute the derivatives? So if I want to take the partial derivatives of this function here, I'm getting this thing in the annoying places right here. Okay, so if I want to take the derivative of the root here, the top, I need the derivatives with respect to x and y. That's what I need, and it turns out you could do that by using the chain rule. I'm going to give a few details in here. Here's what is called backpropagation. So often you want to compute the gradient of a function. So it's all the partial derivatives of, for example, in this case is g, with respect to all the variables, in this case x and y. So you want to compute all of those derivatives. So the derivatives can be calculated by going backwards down the tree. So you have to go actually this way. Once you have evaluated, you have to go first and evaluate each of these nodes, each of these atoms. Okay, you evaluate the functions there, and then you use that to get the partial derivatives by going backward. Here's an example that's actually from neural networks. Very often, it's very common to see something like this. This is, for example, the objective function at the end, and y is some function, some real u or whatever, some function that evaluated at z, and then this is just a linear mapping. Really a simplest example of what you have like a neural network, okay? So how do you evaluate the derivatives? Here's the observation. So now I'm going to call these nodes, I'm going to give them a name. So Vn, for example, depends on Vn minus 1, Vn minus 2, and Vn minus 3, the last one. Let's suppose this is the last one you want to compute. Each of these, remember, it depends on x and y and z, or whatever the initial variables are. But I'm interested in the partial derivatives of Vn with respect to x, y, and z, etc., all the variables. How do I get those? Okay, so the first task is to go forward to evaluate the nodes. This is easy, right? You just go and evaluate the nodes one by one by using these dependencies. So this one will depend on these two, this one will depend on that, etc. Then you can come to reach here. Now all the nodes have been evaluated, right? All the values have been evaluated. Now I need the partial derivatives. So if I look at this particular graph here, let's look at this one. Suppose I had evaluated the partial derivatives of these entries here. Okay, these are, remember, I'm talking about the partial derivatives of the original function, Vn. I'll call that f. In this case, it's called f actually here. They have been evaluated here, and I want to evaluate it here. So it's really, you just use the chain rule. So df over dvk, the derivative here with respect to vk is the sum of these three, right? Because all these three, and I'm assuming they are the only ones, will involve vk. So it's the partial derivative with respect to vj times, so this is the one that has been already evaluated from going down, from backwards. And these have been evaluated. I'm assuming they have been evaluated. Okay, and then these are functions that are easy to evaluate, right? These are things like, for example, this derivative of this with respect to derivative of this with respect to this node. So it's really simple. In this case, it would be v, right? Etc. So then these evaluate, and then you're able to get the function, the partial derivative at this node. How do you do this? You have to be careful about the order. I didn't mention topological order. Usually I teach that with these direct methods. But so when you build the house, for example, you say you have tasks, okay, and you say there will be an order in which I can do these tasks. I cannot build the roof without having the pillars, right? And then the pillars cannot be there without having the foundation. This is just a trivial example, but it shows you. So if you have a very big engineering project, you have big project like this, you have all these different tasks. There is a dependency. It's called directed. Yeah, there's a graph that's set up with this dependency. It's called directed acyclic graph. You cannot have cycles. Makes no sense. And then you could say, you ask the question, in which order can I do this, right? And then there's a topological order. So you cannot do one task before the other one. You can do tasks in parallel. That's one way to determine parallelism in doing these tasks, etc. So then that's it with respect to this. These derivatives. I have to keep moving this all the time. All right, here we go. Okay. So then these are called delta J's, delta K's. These are the ones that I'm looking for. Okay, good enough. So that's what I had to say about computational graphs. And this is an example that's really from neural networks. So this is a layer and so on. This is the final function, the objective function, etc. Okay. Now, let's talk a little bit about graph centrality. So I think I mentioned this earlier. See if there are any questions about this topic first. So this is very common. This is one of the things that made actually neural networks doable. Okay, it's the fact that you can compute derivatives this way. It's really the backbone of neural networks. And the idea again is old, but it was exploited for neural networks. Graph centrality. So I mentioned this earlier. This is a set of methods that will allow you to determine the importance of a node. All right, that actually could be something else. It could be the importance of an edge or whatever, or subgraph. But we're restricting our session here to the importance of nodes, of vertices. There are many such notions that have been defined, and there is the early work that's in the 70s defined these things for essentially networks of networks of people, networks of social networks, right? Okay, so let's look at this thing. So I'm going to give you only the ones that are the most important ones that are that there are many other ones. I mentioned one at the very introduction yesterday. This Bonacci's centrality. There's a couple of other ones that are similar. So the simplest one you can imagine is the degree centrality. It simply says that a node is important if it has a high degree. So that you cannot imagine easier definition than this one here. So by the way, I'm going to try to move this again. Okay, so the scaling both here and here is actually not too common. I did that in the past, but for example, MATLAB doesn't have the scaling, it's just one. So this is a scaling to take into account the size of the graph, but it's not too common. So the degree centrality is simply the centrality that associates with each vertex its degree. the closeness centrality is the following one. It's the inverse of the sum of the distances between V and W. So you're looking at the centrality at V, okay, and it's given, if you take all the paths, okay, all the paths from V to all the nodes. So you take V is fixed, and W is all possible nodes in the graph, except V itself, obviously. Doesn't matter if D to V will be 0. So, and then you take the inverse of that. So it just says simply that the nodes that are close to many other nodes are important. So if the distances are all small, then this would be a larger number. That gives you higher centrality, right? I just want to make sure people understand what distance is here. Distance is the sense of the length of the shortest path. We talked about shortest path earlier. So that's the distance, the length of the shortest path between U and W. I'm going to illustrate that, and then I will talk a little bit about the betweenness centrality. What's nice is I just actually realized recently that MATLAB has all these things implemented. So no, I'm going to go in the other direction here. Oops. Okay, so we're going to clear everything, not to repeat the same mistake as in yesterday. So here is, so degree centrality is not too interesting. It's a very simple one. Let's look at the one that you get from closeness centrality. So there is to implement that, I used my own implementation here of the shortest path, all-to-all shortest path, the Floyd-Marshall algorithm. So let's just go through this a little bit. We take a little bit of time to look at this. So I have a matrix in here, which is called CC, which is simply this is just a adjacency matrix, just like before. These are the IJs, very simple. So IJs without the values, there's no reason to have values. So what I did was load this. Now, this is NZ, the size, the number of nodes I have. Z is, I'm going to set a vector of all ones. I'm going to define a matrix here. So now I define a matrix by using the sparse function. So this is the adjacency matrix. This IJ, the first column will be the I's. The second column will be the columns, right? This is IJ, remember that the two columns. Then I add the ones. I cannot escape that. I have all the ones. And now I have the matrix B, which is a sparse, which has this value, non-zero value for every IJ that's defined in that CC matrix. And now I get a graph for this matrix with the graph, the MATLAB function, and I plot it. So let's do that here. And say test Floyd. That it will just give you this matrix in here. I have actually a couple more matrices, but let's stay with this one here first. All right. Now let's look at the rest. So I paused, and then here is the algorithm here. It's actually interesting. The first thing I do is define a distance matrix. So what I would like to do is get the distance between every node to every other node. So I need a matrix, right? I need the matrix D, n by n matrix, where Dij, D of ij, is the distance between I and j. That's what I'm going to construct. So I'll start that matrix by putting infinity wherever I have a zero, where I have a zero. So where there's no edge, the distance is infinity, right? There's no, initially, that's what you have. Otherwise, you have a 1, distance of 1. So the initial, so if I do only take the original matrix, that's what I do. I use this matrix in here, which is a little complicated to understand, but it simply adds, puts an infinity The infinity form is n plus 1 because you cannot have more than n plus 1 distance in here. So it's n plus 1 for every node, for every edge that, that doesn't exist, we have a 0. Or you could put just the 1 you had before, that's in here. That's how we start the D. Now D has been set. I'll go through this loop, these 3 loops in here, and that's this Floyd's method. It simply assigns Dij to the minimum of the current distance, and the distance you get by going through K. Remember what we saw earlier with this multiplying matrices? This is very similar. So I'm going to set the distance this way. So does this remind you of something? These 3 loops? Tim mentioned a lot of examples like that yesterday, right? Examples where you have, it's a computational. If I had here Dij plus Dij multiplied by Dkj, you would be exactly a matrix vector product or something similar, right? Or Gauss elimination. Yeah, you had a comment?
Yeah, well, it's Kij is the outer loop, so it's
yes.
Not IJK. So this is like an outer product.
Yeah, exactly. It's exactly the outer product form. Yeah. So, right, yeah. So you have the thing that usually, when you have this Kij loop, I associated it with Gauss elimination, where you change I call this Kij version, okay. But actually you could also think of matrix products, where you take the matrix A times B is the sum of the columns of A times the rows of B. So that's the K loop. So K column of A times the K row, the Kth row of B. You add all of those rank 1 matrices and you get the product of AB. And that's exactly what you do here. If I were to replace this by a plus and this by multiply. So the same constructs come back. There's a strong association between these sort of matrix computations and graph algorithms. So this is the Floyd-Warshall algorithm, okay? And this will compute the distances. And now once you have those distances done, what I will show the matrix D. I replaced, by the way, diagonals by zeros. I don't care about those. And then I will show this thing here. So this is D times 1. This is the sum of all the entries in the same row. And I invert that exactly as in this definition here. So 1 over the sum of the entries in the same row, right? That is what this does. So this is division, component-wise division. And then I will display the MATLAB computed one, right? Okay, so let's do that. If I do plus thing, it will give me, this thing is what I'm computing myself, and this is computed by MATLAB. So it's the same thing. And if you look at the graph, I'm reading the wrong one, okay. All right, here's the graph. If I show you this graph without looking at the centrality, let me hide that from you. What node is the most important here? What are the nodes that are the most important ones in terms of distances? I guess it's going to be probably these 2, right? It's closest to most people. So let's verify that and see if that's the case. So these are 2 and 3. 2 and 3 are the ones that have the highest numbers. So that's between the closeness centrality. Any questions so far? Okay, yeah, thank you. Maybe it should go a good idea. The suggestion was, there was a suggestion from the chat to say, if you put this at the bottom, maybe it would be less often on the way. It's probably true, actually. Because my slides has some footer that's totally useless. So that's a good idea. But now I get this thing here on the way. Let me put it on the right side. All right, we'll try this one and see what happens. Okay. Okay, so good enough. Now, the one thing that I wanted to add is the betweenness centrality. Tim mentioned that yesterday, it's a little more complicated. It's actually quite a bit more complicated. So there's two phases and so on, but I didn't implement that. But I will show you what between the centrality, how you can get that in MATLAB. So I'm going to say just centrality. Okay, so centrality. Give me centrality of the graph G, and I just have to give the type of centrality, and it's between us. Okay, and you will give me the centrality. This is what happens. You get that, but you see, the number 4 is 0. Why does it mean no cancel? Of course, what's going on here? Number 4 is 0. There are no shortest paths that go through 4. Actually, I was going a little too far. I didn't define centrality. Yeah. What's going on here? Yeah, sorry. Screen sharing is paused. Why is it? It's paused. Sorry, I see that it's mute for turning and how do you say and pause and pause. I must have touched the button and inadvertently I forgot how to unpause this thing. Yeah. Okay. Thank you. Yeah. That's just really. I must have touched the button inadvertently. Sorry about that. Okay, yeah, so let's go back to this thing. Between the centrality is a little more complicated. So if I look at this graph here, for example, I could ask the following. Let's look at this node, for example. I could take all the shortest paths you can imagine in the graph, and then those that pass through this node. Okay, and so, and then you come up with a definition that's based on that. So you give the importance to the nodes that that have a lot of shortest paths that go through them. And the definition is really simple. So it's given V, it's the sum for all pairs. You have two entries here, U and W. Okay, so you take all the paths. Sigma is the sort of it's a number of shortest paths that from U to V, W, from U to W, you have to, there's no other way than going through all the possible pairs that pass through V and those that are regardless. So you take all the possible paths from U to W and you count them. All right, so it's just counting the number of paths from U to W that go through D and those simply from U to W without ignoring the fact that they pass through V or not. And you add these up. Here's an example. Okay, so you have to list, this is a graph. I have to list all the possible pairs and there are, of course, and you can have a, you only have to consider one direction, A, B, A, D, etc. So all the, from essentially like looking at the upper triangular matrix in this case. So all pairs with the second one being a higher number than the first one, which is symmetric. So now the number of paths that go from U to V, so if U to W, from A to B, that go through V. V here is C. You know, in my selection I have, V is C. V is this one here. This is what I'm looking for. And from A to B that go through C, there is none, obviously. A to D that go through, so for all of these actually here, it would have a 0. For all of these that go from A, we have a 0. B to D, you have a 0, and doesn't go through C. B, so I'm looking first at this column here, okay? And then this is just the other ones. So from B to E, there's 0, B to F. B to F, there's a shortest path of line, the shortest path here that go from B to F of length 2, this one here. So this, you have a 1 in here. And then D to E, again, you have a 1. This is the shortest path that go like this. But actually, there are two of them here. Okay. Sorry, no, this is 3 and 3. So D to E. D to E, you have that there's two shortest paths, but only one of them goes to C. That's actually what you have here. And then you complete that by taking all the shortest paths from U to V. And then you can see then you get the ratios and add them, and you get exactly that number here. Okay. So CC is this one here, etc. So that is how you compute it. It's not an easy calculation. By hand, you can see it on a small example, but you have to organize it differently. Eigenvector centrality, let's see how we're doing on time here. Wow. Actually, so I will just talk about this briefly, and then this afternoon I will talk about PageRank. I think it deserves a little bit more time. So eigenvectors, eigenvalue centrality or eigenvector centrality is based on very simple assumption. So there's this notion of prestige of, so if you have if you have n nodes, each with a measure of importance, a prestige, right, PJ, and the principle is that the prestige of I depends on that of its neighbors. So you have I and the neighbors, and then you associate, so you take the sum of the xj's, so the multiple of the, so some multiple of the prestige of the neighbors, which is given by this one here, that has to be equal to xi with a certain scalar. So it's proportional to xi, the prestige of xi. So the prestige of xi is proportional to a combination of the prestige of my neighbors. That's how it goes. And then it's an eigenvalue problem, and then it's, and you know, you can, Frobenius theorem also comes at play here, because you can guarantee that these are going to be non-negative, and etc. And then I'll talk about PageRank centrality, and I think I'm going to close it for here for this morning. So there's a question here: if the graph is not connected, the closeness centrality becomes 0. If the graph is not connected, actually, this is a good question. If you have a, suppose I didn't have these edges here. Okay, so if these edges were not there, so you have disconnected the graph, right? So what is the centrality? The graph, so they're talking about the close. Oh, this is closeness centrality, not even the closeness centrality of a node. So it's one of the distances. No, actually, the closeness centrality would be, you can define it without too much trouble, because there are some distances here. It would be, we have very poor, this will have a low importance in that case, but it's still defined. It's not going to be 0. The betweenness centrality has an issue in this case, because you cannot, there are no shortest paths in some situations, for example, for this one, that go through A if you remove these nodes, completely out. So the betweenness centrality of A and B, if you had these nodes, these vertices were not there, the edges were not there, would be 0, both of them. So yeah, I mean, the definitions are quite simple, in fact, in spirit. Let's see if there are any other ones here. Okay. Any other issues? So we're gonna stop here, and I will talk about then the definition of PageRank and how this is used to define centrality. But initially, it was defined as a means of defining the importance of a node in a graph, and that's, I mentioned last time, that's how Google actually started, right? They had at the time we had many different browsers, and they were trying to figure out a way of getting better than the others, and Google won. Okay, that's how it works. All right, any questions? I'm going to adjourn here. I'll see you back this afternoon if there are any questions I can answer or comment on. Or good. Okay, thank you all.